Well, thank you, and thanks for being still here. I just realized actually that there are pretty few talks during the workshop that will be about statistical mechanics. So maybe, so thanks even more for listening to what I had to say, even though there are fewer connection with next week's workshop. Okay, so yesterday I started talking about the thermodynamic limits, and I told you this is a term that has two meanings. The general meanings means that we send the number of particles or the volume to infinity, okay? And then in some papers, this has a specific meaning, which is proving the existence of a certain numerical limit, which is in terms of the partition function. Okay. So that's really a numerical value. And as I mentioned at the end of yesterday's lecture, there's another problem which is related. It's not equivalent. There is no clear implication from in one direction or the other, but that feels more difficult, which is proving existence of infinite volume, or infinite or limiting whatever systems. So maybe let me give you an example of what I mean by that. Let's say we are working with Ising 1D, the classical Ising 1D with nearest neighbor interaction on a piece of the one-dimensional lattice. So for fixed n, or maybe that's okay, it doesn't matter. So I have z, and I'm looking between -n and n, and at each site between -n and n, I have a spin. Okay. So there's the state space is well, the spins can be -1 + 1 to the power -n, okay, and then I have Hn, which is the Ising energy. It's I can write it down for of si plus 1, and there's minus here. So that's si, if that's I. Okay. And then there's a Pn beta, which is the canonical ensemble. And maybe I should write it here. So Pn beta is, well, it's a measure on phase space. So it's a measure on -1, 1 to the -n. Okay. And this is all well defined, no problem. But then comes a question that doesn't look so easy. Is there a limit of Pn beta as n + 2 + infinity? And the reason that the question is, maybe one reason that the question doesn't seem that easy to solve is that it's not even clear in which sense the limit should be taken, right? Because these probability measures, a priori, they live on different spaces, okay? But we could think, okay, that P and beta, they all live in some maybe product, or they are measures on some product space, maybe like this. And in some sense, because we can always include, obviously, we can include this space into this space. Okay. And so now they live on the same space. There's a question of the topology that I want to place here. It seems like the right choice would be some kind of local topology, so that it's compatible to have several to have various values of n living in the same space. And so that's an example with Ising. It doesn't have to be restricted to lattice situations. If you have a continuous system living in a big box of, say, size square root of n, and you have n particles here, and they have some interaction potential W, then you can form, so you can still do the same. The phase space will be here. It will be the square minus square root n to the power n. Okay, and then you have an energy Hn, which is just the sum of all interactions, so of all pairwise interactions, and then you will have a canonical ensemble. Okay, and then same question: is there some limit for this quantity? Because I can always see this phase space as being included in, say, R2 to the n. So all my canonicals ensembles, they are in. I think you got the message, right? To the n, but they can all be seen as being part of P of R2 to the Z or to the n. I don't know. There are various ways that you could try to make sense of the question of the existence of a limit. Okay, so I'm not going to say much more than this is a question that matters and it's difficult. So it's actually very difficult in general. It's very difficult to prove such limits. So it's difficult to make sense of the right notion of a limit. Then it's hard to prove the limit. And I want to insist, even compactness is hard. Can be hard. So even proving the existence of limit points can be challenging. Okay, because there is no, it's just the natural topology that you want to put on these spaces in order for the question to make reasonable sense. They lack compactness, so it's hard to treat. Okay, so that's just as I said at the beginning, this is a kind of a message to my younger self. It's not to be surprised that such problems are difficult, and that people have hard times making sense of the right question and then solving the question that they want to answer. Okay. It's much harder than proving thermodynamic limits in that sense. In general, of course, it depends on the problem you're studying. Okay. And actually, you may want to, in order to overcome this difficulty, you might need some averaging. And that's what people do in statistical mechanics, and that's fine. Another message is that's fine. That is a common principle in the statistical mechanics literature. What do I mean by some averaging? Well, people take averages, okay, and the point of taking averages, if we think in analytic terms, is that it smoothens things out usually. Okay, well, for statistical mechanics, it makes your life easier. So what could be here? How could I illustrate this notion of averaging? Let me go back to I don't know, maybe to the 1D Ising problem. So let me draw a larger version of it. Okay. So this was this is the finite n system. Okay, I have a spin at each side. The natural topology on -1, 1 to the z, say, because as I told you, if I need to see all these phase spaces as being subsets of the same large space. Okay, so the natural topology would be a local one. Okay, and so proving convergence of my object would really mean to say, okay, for a fixed, say a 10 to the 10, a minus 10 to the 10, 10 to the 10, I know what happens for a fixed large box. I know what happens inside, and I don't really care what happens outside. Okay, that's it. Like for fixed epsilon, proving convergence would mean studying a large but finite box and then sending n to infinity. And obviously that's hard to do because it means all the information you have is in some large but finite box, and then you're sending n to infinity, so you're losing the vast majority of the information in your system. Okay, so this is you're not giving yourself the right tools to work with. Okay, what happens if you're average? Well, it means you're changing your observable. Instead of looking at the spin config in a large but finite box around 0. This is 0. It should be a spin. Okay, you take averages of that under translation. So instead, you still have minus nn, and this box of size minus 10 to the 10, 10 to the 10, you move it around and you take the average. Okay, so you're looking at what do you see here? What do you see here? What do you see here? And so on. At each time, you see some spin configuration, okay, and you average your observations. So look around the whole system. So you look around locally, but around the whole system. And then take an average. Okay, so you look at the system locally on average. That's a better observable, and that's what people call in statistical mechanics an empirical field. And that turns out to be a better or a nicer observable, because it allows you to capture some of what happens everywhere, but only on average. So of course you're paying some price. Okay. And there's more compactness. And it's nicer to work with. Okay. It has benefits. But of course it's less precise because you're averaging, so you're losing the information of where exactly did you look. Okay. So if you hear people talking about empirical fields, it means that they had such a problem, and that's how they tried to overcome this problem. Be benevolent with them. They are not just looking at an observable out of the blue. It's really something that people like to work with, and there's some motivation behind. Okay, so for example, if you work with such observables, it becomes easier to prove existence of limiting points, and maybe you will even be able to prove the existence of a limiting point process. So you may prove existence of limit points or of a limit. So you have this infinite object. So the limit will be a probability on some infinite configurations, points or spins configuration. And then the question becomes, can we describe such limits in physical terms? Right, so, and to illustrate what I mean by in physical terms, let me remind you of the physical descriptions that we had for the finite systems. So recall that for finite n, the canonical ensemble, we could look at it in different ways. We could look at it, it had an explicit expression of the form, well, no, it's exponential minus beta times the energy divided by some constant, the volume. Okay, so that was one possibility. It was actually the way we introduced. Okay, but I mentioned I think during the second lecture that it has a variational characterization. It's the minimizer of this quantity. Remember, so there's mean energy, and then there was the relative entropy with respect to the reference measure. Okay, and I told you it's a not completely trivial but doable exercise to prove that this functional defined on the space on the set of all probability measures on phase space, it has a unique minimizer which is given precisely by the canonical ensemble. Maybe I could add, that's also something that I mentioned briefly, that it's also the equilibrium measure for a natural dynamics, stochastic dynamics that looked like, it was dxt equals minus gradient h dt plus something like that, dt. Okay, so there were several ways to talk about this ensemble. Okay, and I realized actually that I avoided using the one keyword that is used all the time in statistical physics. So this canonical ensemble, this measure, is called a Gibbs measure. It's called the canonical Gibbs measure. I don't know how I managed to avoid using this word because that's the one word that is used the most frequently. Okay, so canonical ensemble, if you hear canonical Gibbs measure, it's exactly the same. And it will prove important in a minute because I'm going to talk about infinite Gibbs measures. And if I haven't told you what finite Gibbs measures are, you may not see the point really. Okay. So I have several characterizations of these finite volume Gibbs measures. In which way could I talk about infinite volume Gibbs measures? That's if I know that they exist because I've solved that problem, how could I talk about them? And that's actually a central theme of the theory. Okay, and in order to talk about that, I'm going to start with an easy case. It's the case with no interactions. So it's really So I won't spend too much time on it because it's really just talking about the Poisson process. But maybe in a in a different slide. Okay. So what do I mean by the case of no interactions? Let's take some box lambda n with volume n. You can be in any dimension. I draw in dimension 2 for obvious reasons. Okay, and draw n points ID uniformly. Okay, so that's a statistical physics situation where there is no interaction. Just these are just free particles. Okay, so in that situation, the thermodynamic limit is simple to solve. Okay, yes, the thermodynamic limit exists in all the senses that you want. Okay, so well, you have to be a little careful. So the partition function, you want to divide by n by factorial n because they are undistinguishable. Okay, and so this will, if you take the log of this, it has a limit, and divide by n, it has a limit. Okay, and the limiting point process exists. The limiting process exists, and that's the Poisson process on R2 on RD. That's actually the of if you want to be precise, you should say of intensity 1. It has on average 1 point per unit volume, and that can be taken as a definition of the Poisson point process. The Poisson point process. Okay, and there is a variational characterization of the Poisson. Okay, it's not going to be super impressive. It's mostly to introduce a notation and an object, right? So maybe that's too much of a slogan, variational characterization of Poisson. What I mean by that is that maybe I should say, there's an infinite volume notion of entropy. So maybe I should say, on which space does this measure live? That lives on, so it's a probability measure on the space of point configurations in RD. Right, okay. So what you could do is, if I take P, another, and sometimes that's called a point process. Okay, so if P is another point process, I could just look at the relative entropy of P with respect to Poisson. Okay, that makes sense. It's a well-defined quantity because these are two measures defined on the same space. Okay, so either they are absolutely continuous with respect to each other, and then I have a formula for the relative entropy, or they are not, and the relative entropy is said to be plus infinity. Okay, so that makes sense, but it's not a good object. Why is it not a good object? Well, it's almost all the time plus infinity. Okay, it's plus infinity way too often. Okay, so that's not the very if you see this as a distance, it's just almost everyone is at distance plus infinity from Poisson, so it's not going to measure anything interesting. So this is not the right infinite volume notion of relative entropy. What is the right one? Well, it's very simple. You just take P instead, take P, take Poisson, and take lambda big box, compute the relative entropy of P with respect to Poisson, but only in the big box, divide by the volume of the box, and take the limit as the volume goes to infinity. This is called the specific relative entropy. And in many interest, let me just put it this way, in many interesting cases, this is well defined, and it's not as often infinite. Okay, as you can see, because I'm dividing by the volume, so I'm kind of computing the relative entropy per the mean relative entropy, the relative entropy per unit volume. So it's going to be smaller than just the relative entropy, so it might be infinity less often. Okay, and that's the right notion of an entropy for infinite systems. Okay, and the limit exists the way that for actually it's okay for a class of processes for translation invariant processes. If you're interested, you can look it up. Okay, so that's the first important object, this infinite volume notion of entropy. Okay, and it's relative to the Poisson process being the limit of systems with no interactions. Okay, if you do have an energy associated to some pair potential, how could you define, or maybe if you have a pair, let's put it this way, if you have a pair potential, how can you define the energy of an infinite configuration or of an infinite system for infinite systems? Well, you could try to do by unit volume or per unit volume. The same way as we did here, that's the entropy per unit volume. It's the relative entropy per unit volume. So you could try to set h of x, where x is infinite. Let's put it h bar, maybe. H bar of x as the limit of h of x in lambda divided by the volume of lambda. So that's so if you have an infinite configuration with points or spins, doesn't matter, and you want to define its energy, even though it's infinite, one natural thing to try is to take big box, compute the interaction between the spins or the particles inside the box, divide by the volume of the box, go to infinity, send the box to infinity, hope that there is a limit. And typically, if your energy is sub-additive or almost sub-additive, then there is a good chance that this limit exists. Okay, so for short-range potentials, then you have a good chance of defining an object. If you are not lucky and you work with some potential that's weirder, then you may need to work more. Okay, so the existence is not guaranteed. I should make that precise, but for today, let's assume that we are lucky and the existence is guaranteed. Okay. So we've defined two objects, this specific relative entropy and this this energy per unit volume, and they will turn out to be useful in a minute. Okay, so let me go back to my question. I want some description of an hypothetical infinite volume system that would look like what I have for finite systems. If I can make sense of this, and I go back to this expression here, here's a temptation. Maybe infinite volume systems are distributed as E of minus beta h bar of x d Poisson of x divided by some constant. Okay, that would be a reasonable guess. I have an infinite volume energy. I have an infinite volume reference measure with no interaction, and then I just copy the form of the canonical ensemble. It turns out to be that's not the right way. Why is it not the right way? Well, once again, because in infinite dimension, in infinite volume, things do not behave as nicely, and in particular, this measure, well, you either you cannot make sense of it, or if you can make sense of it, it's because you're Poisson yourself. There's a theorem that says if you're absolutely continuous with respect to Poisson and have some kind of mild property, then you're Poisson. Okay, so you can't have a density with respect to Poisson that a density such a nice density with respect to Poisson, it will impose that you are Poisson yourself. So it means there is no interaction. So if you're trying to describe something that has interactions, that's not the right framework. The right framework, or one possible framework that's been used that's been kind of elected as a, if not the right framework, is called the DLR for Dobrushin, Lanford, Ruel formalism. So I'll try to formulate it in 2 minutes because I don't have that much time. The idea is to describe local configurations, or locally maybe configurations, conditionally on the exterior, and describe them as Gibbs measures, as canonical ensembles. What do I mean by that? Let's say I have a 1D system. The DLR formalism suggests that instead of trying to describe the whole configuration with such a density, okay, I'm gonna take a big box, fix what happens outside. So it could be the position of the particles if you're working in a continuous setting, or the status of each spin if you're working on a lattice with spins attached to each side. Whatever happens outside, you fix it, and then you describe what happens inside as some kind of Gibbs measure. So you want to write P of x in lambda, knowing x in lambda complements. You hope that it's some kind of energy of x lambda c d volume lambda of x lambda, something like that. So you hope to write locally your system as a Gibbs measure. So you want to retrieve this E of minus beta times an energy aspect, okay? But instead of trying to do this globally for your whole configuration, you're only trying to do it locally in each large but finite box, okay? And if you have an infinite process and you are able to define the energy in the correct way, such that this is actually true, then you have a DLR formalism for your process, and you're happy because you found some physical description of your system. So if you want to, I have to maybe speed up a little bit here if I want to go to reach phase transitions in 9 minutes. So let me just tell you, this is very nicely explained in the book by Friedli and Bilyk. So if you want a modern textbook take on this, this is very well done. I mean, it's obviously very well done because they are experts on the topic, but I mean, it's pleasant. What I mean by that is it's well done as the reader's experience is pleasant. Maybe that's what I should say, okay? There is The classic reference is the book by Georgi, but it can be a harder read. So I would suggest to first look at the textbook and then go for all the details in Georgi. Okay, and I think it's also done in it's a book that I forgot to put. There's a book by Barry Simon about statistical mechanics of lattice gases, something like that. So it's also done there. So there's a formal. Let me maybe just say that. So this characterization can be encoded in a set of equations. It just, you know, it's just a formal way to state what is written in yellow. Okay, these are the DLI questions. There is no depth adapt to it. It's just it's one way to make it clear and formal what we mean by I can describe the local laws, blah blah. And so you can write DLI equations, and then you can look at the set of solutions. And so if you want here, what is fixed is H. Okay, based on H, you can build these DLI equations, and then you can look for solutions. Okay, and the set of solutions is called the set of infinite Gibbs measures. Okay, and it's a convex set, and the extremal points are the most interesting physically. You know, the more interesting. So there is a whole field devoted to studying the solutions to DLI equations for various potentials and asking whether there is only one solution, many solutions, describing the extremal points and so on. Okay. So that would be an answer to this question: how to develop you know, how to give some physical description that looks like a Gibbs measure for infinite processes. I can say very briefly a word about little b. There is another way to describe. We could also look at minimizer of beta plus specific entropy of P with respect to Poisson. Okay, and mimic the characterization that was true for finite volume Gibbs measures. Okay, so that's another option. Let me call that A. That's B. Okay. Okay. You could also look at you know, dynamics in infinite dimension. That's also a possibility, and look for equilibrium measures, and that's also a difficult topic. Okay, and maybe I should say, in general, you hope for something that is called a variational principle that tell you that B and A are equivalent. It's not proven in general, so it's often true, but not true in general. So often is it the case that solutions of your DLI equations are exactly the same as minimizers of this energy. Okay, so these two ways of describing your infinite systems, if they exist, are in fact equivalent, but that needs a proof, and it's a difficult proof that you need to do kind of each time you need to give a different proof. Okay. So in 5 minutes, I can talk about the most central and important topic of the subject, okay, namely phase transitions. Well, the good thing is that it is central and crucial, but also it's fully defined. So, so what is a phase transition? I don't know. Okay, I don't know. And the term is sometimes overused because people say, "Oh, there's a phase transition. There's a phase transition." It's not even clear sometimes what the phase is supposed to be and how it is transitioning from one value to another. Okay, so I don't know what the phase transition is because I don't know what a phase is really. But what I know is that phases are linked to some kind of order. So what is a phase? I don't know. But it's linked to some kind of order. And so what do we mean by that? Usually you fix an observable. So you fix a function from your phase space gamma to say R, okay? And you call this an order parameter. And then you see whether the average or the typical value, so let me call this O maybe, of O, does it change drastically? Does it change just, or does it change? It changes dramatically as, say, beta changes. And if yes, then you say there's a phase transition. So the archetype is in the Ising model where you have these spins pointing up or down. What you could see is the average magnetization. So the average is there, you just sum them, it's +1 - 1, just sum them all and take the average, okay? You could expect that it's almost 0, which means that there's an equal proportion of pluses and minuses, okay? And if it's strictly positive, then it means that the system points in one direction globally, okay? And if there's a value of the temperature for which you go from, well, typically the system is fairly distributed to typically the system points all up or down, then there's a phase transition. And okay, so that's the archetype of a phase transition, okay? But I think you knew that, so maybe what could I bring you in 2 minutes? Is the following thing. So order in infinite systems is often described by some kind of 2-point correlation. So say you look at spins and you look at 2 spins that are far away and you look at their correlation. So if I know that this one is up, how much do I know that this one is up or down, okay? And order for physicists is often detected as, so if this, and you look at large distance. If it doesn't go to 0, as R goes to +infinity, then there is long range order. Long range order. If it goes to 0 algebraically fast, so say in 1/n⁻⁴, then there's quasi long range order. And if it goes to 0 exponentially fast, then there is no long range order. There's short range order. Okay, so this is one thing that people seem to agree on, is the speed of decay of your correlation that determines a notion of order. Okay, and so once again, if for some value of the temperature you have a certain behavior of the large distance correlations, and if on another value of the temperature you have a different behavior for the large distance correlations, then you say there's a phase transition. Okay, there are other ways to define phase transitions. There are other ways that people say, oh, this is a phase transition. One way is to prove non-uniqueness of Gibbs states, so of infinite, so of solutions to the DLR equations. If your DLR equations have more than one solution, then some people say there's a phase transition. Actually, and usually why? It's because if you have non-uniqueness of Gibbs states, I'll take 3 minutes. I promise you, this is the end of my notes. So I won't keep you much more than this. Yeah, so non-uniqueness can be a sign of phase transition. If you find solutions to the DLR equations that break symmetry, then there is a phase transition. what do we mean by breaking symmetry? Well, take again the Ising model. At finite volume, and you flip all the spins, it has exactly the same density. Okay, so the canonical ensemble, it's invariant under flipping all the spins. If you find a solution of the DLR equation, so an infinite volume process that is not invariant under this flipping the spins, well, it kind of means that it prefers one direction to another. And so you've broken the symmetry between the spins. That's an example of breaking symmetry. And if you break symmetry at some value of the temperature, you have a phase transition. So as a conclusion, and okay, so that's for a spin, but there are other notions of symmetry. For example, if you have a continuous system, it's symmetric under translations. So at least the potential is, right? It only depends on the distance between particles. If that's not the case in the limits, if your system is not translation invariant, then you've broken the translational symmetry and you have a phase transition. Typically, let me just conclude with this. Typically, symmetries are broken at low temperature. Why? Because ground states, they like order. And order might want to, in order to be ordered, you may want to break symmetry. You want to say, you have a continuous system, but you want to minimize the energy. You're placing your points on a lattice. Okay. You have a spin system, but you want to minimize the energy. Then you choose all the spins to be in the same direction. Okay. And then if that's the case at t equals 0, then maybe it's also the case when t is very small. Okay. Whereas for t large, there is so much thermal agitation that you will break. You might recover. Sorry, you break the order and recover symmetry. So this is known. This has been proven for some systems. For Ising 1D, there is no breaking of symmetry. For Ising 2D, there is at some value of the temperature breaking of symmetry, and so on. So there are some results for specific systems. Okay, and there are also some forbidden results, if you want. There are some results that say symmetry cannot be broken in such and such context. So there are, if you want, there are counterexamples. There are no statements that say no phase transition can happen. The most famous one maybe is Mermin-Wagner. That's for 2D and continuous symmetries. I want to insist that this is a theorem that requires hypothesis, and it's not just a God-given principle. Okay, so if you are not satisfying this hypothesis, you might still break the symmetry, because sometimes people overuse Mermin-Wagner. Maybe the conclusions are still true, but it's not proven in all the cases. Okay, and there are some possible, and I will stop here. There are possible subtle transitions. So I'm just going to leave the so exotic transitions. I'm just going to leave the keywords in case anyone is interested. There's the BKT transition, which is said to be of infinite order. In the BKT transition, this correlation function changes its behavior in a very subtle way, and so it's said to be it's a very strange kind of phase transition. I'm going to stop here. Thanks for sticking with me. Thank you for your attention.